Hello, this is Mei-Qin Zhan. Thanks for the symposium organizer to give me the opportunity to give a presentation here. The title of my talk is Backward Uniqueness Properties of a Nonlinear Dynamical System. So here's outline for my presentation. First, we introduce the problem raised by Peter Lux regarding backward uniqueness. Then we discuss the motivation and tools to address the problem. And then we give an example, demonstrate there's no backward uniqueness. And then we also mention that Peter Lux's original work and the time average method used to prove a backward uniqueness problem. And then we look at the log-rest convexity method, and then to introduce the work done by D'Aglia and one use the Dirichlet quotient, and then my own work on that Ginzburg-Landau equation. So the problem that raised by Peter Lux, the backward uniqueness for evolution partial differential equation is a classic problem that initiated by P.D. Lux in that is the 1956 paper, a stability theory for solutions of abstract differential equation and its application to the study of local behavior of solutions of elliptic equations. So basically that they look at the equation, the u prime plus au equal to f in some helpless space. And then Peter Lux that asks the question, can solution of such equation be zero for all t greater than some capital T without being identically zero? This problem is called a backward uniqueness problem. It's a generally harder problem because that the backward Cauchy problem is in general yield post or incorrect post, and the solution that at a earlier time do not depend continuously on their value at a later time. So the motivation of study this problem is basically it will provide help in the study of attractors and the long-time behavior of infinite dimensional dynamic system, and also provide help in the study of asymptotic behavior when time goes to infinity of solution of parabolic equations and inequalities, and then that understand the injective properties of semigroup generated by the solution of a nonlinear dynamic system. Furthermore, so they establish the uniqueness continuation and the controllability property for overdetermined evolution problems. The tool used to study is basically that a log-rest convexity approach, time average approach, and a Kalman inequality approach. So here we look at a simple example to demonstrate there's no backward uniqueness. We start with a simple ordinary differential equation, y prime equal to 10 over 3 x to the power x times y to the power 2/5, y0 equal to 0. And we have general solutions, and then we also have a particular solution y identical to 0. Combine these two, we can construct another solution, y equals to x to the power 10³ when x less than 0 and equal to 0 when x greater equal to 0. In this case, that you can see y is not identical to 0. Then that corresponding that the partial differential equation is du dt equal to plus u plus 10³ t u to the power 2/5. We can easily see utx equals to that t to the power 10³ when t less than 0, and then utx equal to 0 when t greater equal to 0 is a solution. This is certainly is not a solution which is identically equal to 0. And that the classic work by Peter Lux in 1956, he basically looked at the evolution equation of ut equal to capital D plus capital Ku, and then require that K is not larger than the size of gap in the spectrum of D, in essentially that the H norm of du dt minus capital Du is less equal to kt times that the H norm of U. Kt is a scalar function satisfy certain conditions. And in that concrete case addressed by Peter Lux, that the backward uniqueness problem that is equivalent to that that the uniqueness that equivalent to the two solutions of elliptic equation in the unit sphere, which are equal in some sphere, no matter how small its radius, are equal in the whole unit sphere. So that also basically means that the uniqueness of Cauchy problem elliptic equations use the concept of range approximation properties, and then basically means that the solution in a given domain can be approximated arbitrarily closely by solution defined in the given larger domain, which is not disconnected by the smaller domain. And then Lax was able to prove the equivalent theorem that if L is an elliptic operator and solution L equal to 0 has a range approximation property if and only if solution LU equal to 0 uniquely determined by that by their Cauchy data along any smooth hypersurface. So which of course prove the backward uniqueness problem too. And that the tool they use is this basic green formula. And that Lee and Prouder in 1961 and tried to study backward uniqueness among other problems of this heat operator. So that L equal to A minus D dt on a unit disk. So, and AIJ, of course, that the requirement for their work is that the C2 function, which is a very strong requirement, and A is positive defined. And in this case, that if that V is a function satisfies LV squared less equal to CV squared plus C2, the gradient of V that to the squared. And if the t equal to 0, the integration of gradient squared of V is that it goes to 0. And then V has to be identical to 0 if V equal to 0 on the boundary of D. So that's the result on the backward uniqueness. So the proof, the tool they use is basically that look at that norm of lambda to the power negative m times Lu. Lambda is the function lambda t equal to t minus mu for some mu greater equal to 0, m to be a positive integers. And then they prove that there are two key inequalities that for that L2 norm of that lambda to the negative power MLU. So from there, they use this, introduce new function z equal to lambda to the power m of u. So you can think in time average on u, and try that they arrive at that conclusion. And then, of course, that is that later that in 1963, then Argument Nirenberger studied the same problem that a du dt equal to bu equal to 0. And then they introduced that concept of logarithmic convexity. And with some conditions on the operator B, notice the B doesn't have to be self-adjoint, but the U belongs to the domain of a B star and a B. And that the B also satisfies some that the positiveness on the real part. And then they prove the log function that log e to the negative KTUT, that L2 norm, is a convex function of variable s equal to e to the CT. So notice it's not a convex in the original time t. And that's the way to prove it. So they introduced two new functions, v of t equal to e to the negative KTUT, and then they find that define the little q equal to inner product of v to itself, and they show that q satisfies this second order differential inequalities with the help and of this convexity. And then they look at that equation that 1 over I du dt minus a alpha u less equal to phi of t u times that the norm of u. So similar question to that what Peter Lax addressed. And then that the requirement that the semigroup generated by this system satisfies this bounded conditions. T that the norm of capital TT is less equal to k plus 1 plus t to the power L and e to the omega absolute value of t. And then if phi is a non-increasing, and then there's a lower bound of phi of A is bounded from above, and then they prove the u of t is bounded by the value between the UA to the power B minus A divided by B minus A, B minus T divided by B minus A, then times that the U of B value at B to the power T minus A divided by B minus A. And then the corollary is that if U equal to 0 at some point, it has to be identical equal to 0. So that is backward uniqueness problem provided by them. And by studying their that the method, and then Algava realized that the key ingredient is a so-called district quotient. And then again, the problem he studies LU equal to DU dt minus AU. And the requirement for LU is bounded by phi t of the L2 norm of LU is bounded by phi t times L2 norm of that UT, the 2 norm. And that in his proof, the key ingredient is the district quotient, AU inner product between AU and U divided by the L2 norm of that U to the squared. And then when they differentiate that 1 log of U squared, they realize the first term, of course, is the district quotient, and that differentiate the district quotient, and that show that it's greater bounded below by negative 1/2 phi squared. And from there, they can show that a log of t is bigger than that log of u at u of t is bigger than log of u0 plus some other function involved time t. He didn't get the backward uniqueness conclusion, but he proved this decays lower bound for that solution u of t. And that in 1985, Gilia and applied used that different quotient to show the backward uniqueness for that the equations of the form that d phi dt plus VAT phi belongs to H, that and also is bounded by d phi dt plus V phi A phi is bounded below by N for that the 2 norm of V. So here that extended the previous result, and that the key ingredient is defined as the district quotient, that then capital lambda t equal to AT phi t in the product with phi t divided by the phi t in the product with phi t itself. And by differentiate that one, they derive that the differential inequality is satisfied by capital lambda. And then also that after that, then you differentiate again that the log of phi L2 norm of phi, and it turns out negative dt d dt log L2 norm of phi is bounded below by bounded functions, then which indicate that the one is integrable, and which will arrive a contradiction to show that if equal to 0 at some point, you have to be equal to 0 identically. Then finally, that my own work on this Ginsburg-Landau equations. We have this Ginsburg-Landau equations. By introduce a gauge, we can come out with the dimensionless equations. And then furthermore, by introduce that Landon gauge, then assume f is a real valued functions, we're able to further reduce the equation to this simpler equation. And then write the equation in the operator form. So we have d dt ut plus d capital L ut plus r u of t equal to g. And for this function, that we prove that existence theorem if initial delta belongs to the h, that some function of space, and we prove this that the unique solution result for initial value problems. And then we look at the backward uniqueness problems. Suppose we have 2 func solutions and satisfy 2 initial data. If they equal at a sometimes later time, they have to be equal to each other for all time t greater equal to 0. The way to do that is we introduce the omega, which is u1 minus u2, when then we find the equation for that omega, and we write it out in the vector form. And then we show that V is actually bounded by that mu of t times that 2 norm of W, and the mu of t is an L2 function, which is basically the condition that stated in that Didajia work. So, and then we introduce that discrete quotient, and we find that the equation of differential inequality is satisfied by the capital K of t. And also we show that d dt log 1 over that absolute value of ohmic is less equal to k plus a mu of k to the power of 1/2. And from there, we can derive that the conclusion. That's my presentation. Thank you very much.